Hey, Chapin, it's good to get a chance to talk to you.
Thanks, Frank. I'm excited to tell you about what's been going on here.
Well, let me just start by saying congratulations. I mean, this is a big deal that we have been plugging away at for a long time. So it's got to feel great to have been working on this for so long and then have it go boom, here it is for the world.
Yeah, thanks. It does. It really feels great. It's gratifying and it's really exciting because, we're seeing something in nature that, you know, we have been thinking about for a long time that people have hypothesized for decades. And, when we first saw the data confirming what we were seeing, that we were seeing what had been going after, it was really mind blowing. And the whole journey has been, really exciting. There obviously have been moments where we were lost and didn't know what to do. And then there were those moments of realization where we realized, oh, wow, here's the way forward. And so it's been an amazing journey and it's a really exciting scene. It feels like it's a turning point too. It's not the end of the journey by any means.
Right.
It's really opening up a new vistas for us.
Yeah, so let's try and capture that for a little bit. I mean,
Yeah.
you have been in pursuit of a new state of matter,
Yeah.
and we now have confirmed that this new state of matter exists. And it's what's really going to drive our quantum efforts forward. So talk a little bit about like what we've created and then how it compares to sort of this, what I guess, standard
Yeah.
quantum computing, if there is such a thing.
That's right. So, people make all different kinds of QPUs or quantum processing units. Our QPU has a topo core, topological core. So that's a very specific heart or core of our QPU. And the reason we created this thing is because we took a step back and said, we want to make a quantum computer that can solve some of the world's hardest problems. So a quantum computer at a scale where we can simulate chemical reactions, for instance, that you couldn't otherwise simulate. Then we knew that it was going to have to be based on qubits with very special properties. They were going to have to be fairly small so that we could fit many of them on a single chip. We'd have to be able to operate them pretty fast, and we'd have to be able to control them. Because one of the things that people don't always realize about qubits is just how difficult it is to control them. And the flip side of that is how difficult it is to maintain them stable and isolate them from the world. So we knew we needed pretty special properties. And so we went about saying, what is the underlying material that gives you those properties, at least to some extent, inherently in the hardware? And just as people went from vacuum tubes to silicon and then eventually to integrated circuits, as you can make a computer with anything. You can make a computer with mechanical parts, right? The original Babbage machine, right?
Yep.
Adder, you could make it with vacuum tubes. The kinds of computers we have now, it's the same kind of logic you have with vacuum tubes, but the miniaturization, the reliability that you need relied on silicon and particularly the transistor. So we really felt like we had to be building this on the right underlying material. And that's what we went about creating. It's called a topological superconductor, or topoconductor for short. And this is something that people have hypothesized for decades. But no one had really reliably created this in the laboratory or been able to harness it for quantum information processing. And there were a variety of reasons. It required, breakthroughs in fabrication, material synthesis and fabrication, because the path we took uses a semiconductor called indium arsenide. It's a semiconductor that has other applications, like in night vision goggles, for instance, but we needed a special version of it within a particular material stack where it also came in contact with a superconductor, aluminum, which also has applications even in quantum information processing. So it's the marriage of these two things into something that gives you something new, that gives you a topoconductor. And it had to be done with a certain amount of precision. That meaning that it has to be very clean. The interfaces all have to be very good if you want to get the best of both worlds between the superconductor and the semiconductor. And in order for us to know what the right combination was and how to make it, we actually needed to be able to simulate all these things.
Right.
And ironically, we would have had an easier job if we had a quantum computer of simulating all these, these material stacks. We don't have that, but we developed simulations that we could run on the classical computer. And those breakthroughs in simulation and design, in fabrication and synthesis, and also in measurement technique enabled us to get here.
Yeah, that's we've been in some meetings together where people have sort of joked about like, our gosh, our jobs would have been a lot easier if we had
Oh,
a
yeah.
quantum computer to simulate the materials we needed to create a quantum computer, but we just had to make them ourselves.
No, it's funny and ironic, but it's true.
All right, so tell me a little bit more about the material that we're using on it on this and why it's different and important. Again, relative to some of the things that other people are doing in the space.
Yeah. So superconductors are this actually really amazing. So let me actually take a step back. So we learn in school about different phases of matter, like solids and liquids and gases.
I
And
got it. I
you know,
remember. I'm there with you. I got
okay,
those three.
good. So, as if you take a liquid, as you change the temperature or pressure continuously, its properties change continuously. Like the density changes a little bit, the viscosity changes a little bit, but then you get to a phase transition point, and at that point, things change discontinuously. So you go from a liquid to maybe a solid, and the solid no longer flows. Or you could go to a gas, and the gas has different properties. So there are these discontinuous points, which are phase transitions where it goes from a liquid to a solid or to a gas. So that we're all pretty familiar with. It turns out that there's actually a more refined classification of phase of matter because, if I look at a solid, not all solids are the same. Some are magnetic and some are non-magnetic. Okay.
Mhm.
And they have different applications. Some are insulating and some are conducting. Again, you use them for different things. It turns out that there are some solids that are superconducting. And that's a really remarkable property wherein, unlike most metals, in which there's some energy dissipation when you run a current through it, superconductors can conduct current dissipationlessly. And that's a remarkable property of superconductors. And people use superconductors for making qubits. That's actually one of the, sort of the kind of, those are some of the OG qubits are using superconductors
Right.
because of and the reason is in a superconductor, the electrons, the individual electrons, which is what's responsible for carrying electrical currents, they actually form pairs, something called Cooper pairs. And those Cooper pairs move in lockstep together. They actually move in essentially the same quantum state. And that quantum state enables them to carry current dissipationlessly. It gives you a big energy, or it gives you an energy difference between having an even or an odd number, because in the odd case, there's always one that's unpaired.
Right.
And it also is the basis for some types of qubits, but essentially because the current can run one way or another way. And those two different quantum states can be, superposed or used to store quantum information. Now, a topological superconductor, it turns out that there's actually even more than just one type of superconductor. A topological superconductor, topoconductor, is a special type of superconductor which has an additional property. It has all those properties I just mentioned about being able to having pairs and being able to carry current dissipationlessly, but has one other property, which is actually it doesn't mind having an odd number of electrons.
Mm.
Okay. When you get your head around that, it's actually pretty surprising and pretty weird, because this is a state in which everything pairs up, and yet a topological superconductor can accommodate an odd number of electrons without having any noticeable unpaired electron anywhere. It manages to hide that unpaired electron through the ground state of the system. And now it also necessarily has, in addition, if I have a topoconducting wire, it actually has what are called Majoranas, or Majorans. So the technical term is a Majorana zero mode, but we just call them Majorans for short, which are basically placed at the end of the wire where there's zero energy states. So you can change from even to odd by actually adding an electron there at the end. It then goes into the wire and it's completely spread out and delocalized. And there's no place in the wire that you could trap or localize an unpaired electron. And so this property of being able to accommodate equally well an even or odd number of electrons is really the special property of a topoconductor. And it's also why it's such a great qubit, because the thing that you are using as your qubit, your degree, your register, your 0 or 1 is even or oddness.
Right.
And it's a thing that you cannot measure locally. In the other ways you use a superconductor, running currents through it or superposing ground states and excited states or some oscillations of the current of pairs across what's called a Josephson junction. Ultimately, there is something local there that you can measure. And that's also why the environment can effectively measure it and collapse it like Schrodinger's cat.
Right.
Which, I mentioned Schrodinger's cat. It's the 100th anniversary of Schrodinger discovering this equation. And kind of remarkable coincidence there. But so anyway, coming back to the main point, that very special property means that this is a very well protected qubit. The information is extremely well protected. Now, you might, upon hearing that, say, well, that sounds like too much of a good thing because, it's great, it's well protected, that, the unpaired electron is spread out over the wire, and there's no place I can find it. Well, then how am I going to do anything with it? How am I going to even know whether it's an even or odd number? And we have a way of doing that. It's a very, it's a pretty cool way. It's mentioned in this, it's described in detail in this Nature paper, and we just discussed it in detail at this Station Q conference we just had in Santa Barbara, the 18th and 19th of February. And the idea is when you have, one of these topo conducting wires, maybe an even or odd number of electrons, you can couple it to something called a quantum dot, which you should just think of as a very small capacitor that can hold charge. And that charge can go, and a single electron can go from the quantum dot, go in one end of the wire through the Majorana, come out the other end. And in so doing, it actually counts whether you have an even or odd number of electrons. You've got to do something non-local. You can't just look in one place. You've got to go what's called an interference loop. And when you do that, you do that counting.
Yeah.
So that's how we do it. And the thing that's remarkable is, we can do it, and we can do it really accurately and fast. So it's a very effective measurement technique. It's a measurement you do. It's actually like the linchpin of how we process information. It's also further confirmation that we really know how to harness this state of matter. And so that measurement technique, when I said the advances were in like simulation, fabrication, this measurement technique is one of the advances that we're really excited about and honestly proud of. And so demonstrating that technique is really enabling. And then there's a more advanced version of it, which we've just discussed, which is actually as you build more complex devices, you may have multiple wires because, qubits and multi-qubit systems are going to be more complicated. And what we demonstrated is, in fact, you can do that measurement across multiple wires with Majoranas sitting on two different wires and an interference loop where you're counting even or oddness across wires, which actually puts you in a superposition of states in each individual wire. So there's a number of cool tricks that we can play here, which are all different types of quantum information processing based on the state of matter.
Yeah. So one of the things that I've heard as we think about why it matters is that this qubit that we have, this topological qubit, I'm going to oversimplify, and you can tell me how wrong I am, is that it's smaller, it's more stable, it requires less power, and it requires less error correction, and it's more scalable, I think. Are those
I think you've got most of the pieces of the properties, but let me refine that a little bit, which is usually in a qubit, you have painful trade-offs you have to make. You can make a qubit more stable, but then it's harder to control potentially because you've isolated it really well. In some cases, it's really big. There's a way that you end up making it more stable, or in some cases, the operations are really slow. That was the way you made it more stable. So you can make a qubit that's really good along any one metric, but what's hard to do is to make a qubit in which you don't have to make those painful trade-offs. And I think that's really what's special here is there's a parameter which is sort of how robust the strength or quality of the topological phase, which we call the topological gap. It's an energy gap, and that energy scale relates to a time scale, and a length scale, and a frequency. And when that parameter is large, it means your qubit's really robust, low error rates. It also means it can be small. It also means it can be fast. And so there's all the cool thing here is those all head in the same direction rather than opposite directions. It's not like a seesaw where you help on one and then you hurt the other. They actually all go together. That's really unique and powerful.
What is the next step for the team now that you've made this discovery?
Yeah. We are making more complex devices. I would say there's there's two axes. One is we're making more complex devices. So we have, our first QPU, Majorana 1, with a Topo core. We are now making more complex devices. We have 1 qubit, an 8 qubit device, and then we're looking at, devices with more qubits. More complexity gives you the ability to, do richer computations, heading towards and beyond error correction. Okay.
Yeah, and so we're saying that like with this new technology, we can scale to 1 million qubits on a chip the size of like a watch face.
Yeah,
which is pretty impressive.
That's what's really exciting, is that the qubit is small. It's less than 10 micron by 10 micron aside, and a lot of qubits really are quite a bit larger for one reason or another, usually having to do with the trying to make them stable. But interestingly, they're also not too small, because too small is also a problem, because when they're too small, it's actually hard to get all the wiring in there to do all the control. So we've really hit a Goldilocks, scale, where they're not too small that you can't do anything with them, but they're not large that you end up needing a warehouse to make a useful quantum computer. And so I think that's one of the really exciting things. But without a doubt, when we looked early on at how we were going to build a quantum computer, we really focused on scale. And when we looked at that, we really architected, our roadmap so that we could make this small and not be dealing with, warehouse-sized cryogenic systems.
Right. What is the number 1 million? Why is it important to be able to get to that number of qubits on a chip?
Yeah. So I would say that the answer is, if you want to do really long computations, so computations that are trillions of steps, right? Or maybe even hundreds of trillions of steps, you are going to need extremely stable logical qubits. So those are the fundamental algorithmic building blocks that you build up from physical qubits. Those are going to require hundreds of physical qubits per logical qubit. It will be less if your underlying physical qubits better, which is our plan, but nevertheless, it's going to be hundreds. You will then, with those, with those logical qubits, you're going to need, the first point at which you'll really start being able to simulate materials that you can't otherwise simulate is with a few hundred, 100, let's say, bare minimum, and then a few hundreds in chemistry into thousands of logical qubits. So when you really think about hundreds of thousands of logical qubits, that gets you towards and beyond 1 million physical qubits. And actually, that kind of brings me back to a subject that I really spent a lot of time earlier in my career studying, which is material science of things like magnets and superconductors and complex materials, which have these properties that could be so helpful for whether it's motors or batteries or maglev trains or electrical conduction and or power transmission. These materials that we really don't understand all that well, and which we can't simulate very well with an ordinary computer, but which quantum computers would be, it's one of the killer apps for a quantum computer. And so I'm really excited actually to be able to return to some of those questions that I, was thought out a lot early in my career, but didn't have the tools to solve, and coming back to them with the right tools would be really amazing.
Yeah, you had to invent a new thing in order to answer the questions that your old self was asking. So the circle comes around. I love it. So you started off this conversation by talking about sort of like the changes in computing architecture from mechanical to vacuum tubes to single chip to integrated chips. So like I'll ask you a question and you can give me a yes or a no answer. Silicon is to modern computing or von Neumann architecture as this chip is to the quantum era. Yes or no?
Yes. Having said that, when we look at the scale that we need for a quantum computer, to me, it's very clear we needed something different. That we need the first generation of qubits were great, but are not going to get us to that scale. They are based on systems which we have been experimenting with since the 80s, or in some cases the 70s, and doing lots of great uncovering lots of great fundamental physics, whether it's atomic physics or physics of superconducting devices, useful for sensors, lots of great applications. It would be surprising if that first generation turned out to be the thing that got us to scale. Just as it would have been surprising, for our vacuum tubes, the thing that you try, is that going to get you to, to like the phones that we have in our pockets? That would have been a huge surprise and it didn't turn out that way, right?
Right.
So a lot of fundamental, for decades, a lot of fundamental work in semiconductors, understanding semiconductors. What are the intrinsic properties of semiconductors versus which properties are a function of how they were made or the impurities that are in them? A lot of that fundamental work had to happen for people to be able to make initially the first transistor and then better transistors and ultimately the integrated circuit. I think we had to go through that same journey of understanding some of these more subtle states of matter like topoconductors, which have the properties that we need to make, topo core QPUs. And we had to go through that journey. And I think that now that we know how to make these things, that to me seems like a turning point.
Well, I just want to say again, congratulations to you and the team. It's a massive scientific breakthrough, and it sets up so well for the next set of months and years to come until we get to a fully functioning quantum computer that can solve these big problems we all think about.
Thank you very much. These are exciting times, and I'm glad to be able to share some of the excitement with you, Frank.
Okay, great. Thanks a lot, Chapin.